Okay, welcome back to the third part of this five-part tutorial where we derive the critical t-value for students' t-distribution. In this third part, we're going to look at the cumulative distribution function for students' t-distribution. And we're also going to look at its connection to what's called the regularized incomplete beta function. That is I sub z of A and B. Now, quickly before we go on, I just wanted to note, if it was not made clear in the previous video, this term here gets divided up as this product as you try to take v over 2 out of the expression. And you can see that with some simple algebra. This is simply some margin work, and it's not particularly relevant. But I just wanted to make that clear before I move on. Okay, so recall last time that we were looking at students' t-distribution, that we derived from first principles an expression for students' t-distribution. And that probability distribution function had this representation. So now we're going to look at the cumulative distribution function for this probability distribution. And if we return again to our schematic, we can get some insight as to what we're interested in. So, make that a little too long. So, we have a unimodal fat-tailed distribution here. And this unimodal fat-tailed distribution is students' t-distribution. And at either end of this distribution, we can look at the quartiles. There's a positive and a negative, and these will represent the critical t-values. Recall that this term, this area here, is related to our confidence interval, which we're seeking. This area we'll call A of t given n, where n is the degrees of freedom for our distribution. V, not n. V are the degrees of freedom for our distribution, and v is equal to n minus 1. Now, if we recall, this A t given v, is simply the integral of our distribution between these two limits. And we'll show that this area is actually equal to 1 minus this value here, which is the regularized incomplete beta function. But before we do that, we need to look at the cumulative distribution function. So I'd like to define a few things, explain a few things. We have to note that between negative t and t star, that this gives us the probability that a value less than t, a value t is less than calculated from that observed in the data is merely by chance. So that's the interpretation. And we can also note that the confidence interval is 1/2 that area minus ADA. If we recall that this area here is equal to ADA. So those are some preliminaries. So we're going to move on, and I'm going to show how one evaluates the cumulative distribution function. First off, we need to look at the definition of this A. So the area A t given V is simply going to be equal to 1 over, and I'm introducing a new term here because it simplifies things. That's just the beta function with those two values. Multiplied by the square root of n. And the beta function is I'll define that later, but it's related to the gamma function, essentially. And you can see it up top precisely what it is. In fact, I can show it here. Essentially, I'll do it over here. Beta of v over 2 1/2 is equal to gamma of v over 2 times gamma of 1/2 over gamma times, gamma of their sum. And if you recall, gamma of 1/2 is merely 1 over the square root of pi. So that's just a simplification that we make. Returning back to the integral, it's between these two values here. And it's of this integrand you could say dt, and we're going to show that that's equal to 1 minus this regularized incomplete beta function, So rewriting this, we can rewrite this as because it's a symmetric distribution, we can go from 0 to t star and just double it, which makes the calculation a bit easier. We're going to rewrite the integrand in this fashion. And this is all to set up to show in just what way the cumulative distribution function of student t distribution is related to that regularized incomplete beta function. So we're going to make some substitutions as follows. We'll call W v over v plus t squared. And then for t being positive, which it is, we're going from 0 to a positive value, we get that t is equal to the square root of v over w minus v. And dw dt is simply negative t v over t squared plus v squared. And that enables us to show that dw is equal to negative 2 tv t squared plus v all squared dt. And we can rewrite this as a product. So we have negative 2t all over t squared plus v times v of t squared plus v dt, which we can rewrite again in various ways, and we can write that dw is equal to negative 2t over t squared plus v, and then we can always multiply by 1, so we'll do that here. We'll get t squared plus v to the negative v plus 1 over 2, and then we're just going to take the inverse of that. That's v t squared plus v raised to the positive v plus 1 over 2, and then again we've got our v t squared plus v dt. And this term in the middle, this product in the middle, simply equals 1. But if you notice, that allows us to rewrite this infinitesimal equivocation, I suppose you could call it that, in this form. We can say that negative v t squared plus v, positive v plus 1 over 2 times t squared plus v over 2t times v over 2 plus, or v, or t plus t to the 2 plus v, the inverse of that, dw is equal to v t squared plus v plus 1 over 2 dt. And if you notice, we now have our integrand on the right hand side. So what does this left hand side equal? Well, if we recall, w is equal to v over t squared plus v. In other words, we can write negative w v plus 1 over 2 times, well, if we multiply by v over v, we're going to get v 2t times w, and then we'll have a inverse. So it's w inverse times w inverse again, dw, and that's equal to the term on the right. And if we combined exponents or like variables with like variables, and then we write out an expression for t, if we recall t was the square root, that square root term, we get the following, which is v over 2 times, and we've got this t term, which is this, which I'm just going to paste here, and that's actually the inverse dw, and it's equal to this right-hand side, which we'll fill in later. And we can pull out this v, and we'll get v to the negative 1/2, and we can bring, well, let me do it this way. So we can write this as this, and we've got 1 over the square root of w squared times v over w minus v dw. That's equal to that right-hand side. And we notice that we can bring out the v, and one of the w's cancels to give us this term. So that's that, and then we're going to get w minus w squared dw, and we can bring out a w again and get w to the negative 1 v squared times v to the negative 1/2 times w to the negative 1/2 times 1 minus w to the negative 1/2 dw. And we can bring this down make the substitution. We can bring this down, make the substitution, such that now our integral is 2 beta of this and recall that we have to do w of 0 and w of the critical t value with an integrand given by this function here, which I'm going to simplify real quick. And this simplifies to this value, v to square root of v, w v over 2 minus 1 minus w negative 1 over 2 dw. And that's equal to that right-hand side, which is our integrand that we're replacing. So now we can put this here and make various simplifications. So for example, we notice that these terms are going to cancel. We notice the 2 is going to cancel, and we're going to be left with negative b, or beta, inverse beta of these two terms, w of 0, w of the t star of w v over 2 minus 1 minus w this dw. And this is a nice result, which I'll follow up on.